Okay, now let's look at the next order, at order lambda cube. So one expects the graphs to be larger here, and it is useful to look at a relation between the number of loops and the number of vertices. When we say lambda cube, we refer to the number of vertices. These are graphs with three vertices, but let's connect this to the number of loops also in order to facilitate the drawing of the graphs. So the relation between L number of loops and V number of vertices. And we use these two graph equations that we used earlier. One is E plus 2I equals N times V for phi to the power N interaction. E is number of external lines, and I is number of internal lines. Another graph equation is the relation between the number of loops, internal lines, vertices. And using these two equations, one arrives at twice L equals N minus 2 times V plus 2 minus E. Okay. And in our specific case of phi-fourth theory, it will be any small n is equal to 4, so it will reduce to V plus 1 minus E by 2. And since we have two types of diagrams with E equals 2 and 4 to consider for looking at their divergences, so this is 2.1 pi. In this case, L is equal to V, and 4.1 pi. In this case, L is equal to V minus 1. So at lambda cube, when we look at the 2-point function, we draw 3-loop diagrams, and when we look at 4-point functions, we draw 2-loop diagrams. Okay. So for the 2-point function gamma tilde 2 at lambda cube will be given by, so let me not mention P here, I'm not being that specific here. So we had this diagram in the previous level, which are, there were 4 diagrams. So you have to add one more loop to these diagrams and find out all possible ways of doing that. You can check here this vertex 1. It is at order 1, but this vertex is for a 2-point function, and therefore it is one loop also. And if you remember, this is a vertex coming from the one loop diagram. Which is given by this one. So that was the vertex that cancels the pole for this diagram. So this is this vertex 1, since it's a 2-point vertex, 2-point vertices, I mean counter term vertices are denoted by cross, and cross 1 means at order 1, at order lambda to the power 1. But since L is equal to V for the 2-point function, it is also one loop. Similarly here, this is a 4-point vertex. A 4-point vertex is given by a dot, but this dot has 2 because it has to be one loop, but lambda order 2. So order lambda square, which is why it is denoted as 2, but from the point of view of counting loops, it is one loop maintaining this relation. So that is how for all these diagram you can check these two relations. But now for this lambda gamma tilde 2 3 at level 3 or at loop level 3, you have to add one loop to all these diagrams, and you have to find out. So I leave that as an exercise. I'll give you some examples. So for example, this is one diagram that appears there. You just add one loop here. You could add this loop in a normal way with an original vertex of the theory, but you could also add the loop by adding cross vertex at level 1. So that will be a 3-loop diagram or lambda to the power 3 diagram. Okay, so you could also just like you replaced this loop by this one, you could also so this bottom loop can be replaced by, because bottom loop actually is a 4-point vertex. So this loop can be replaced by so that's also a valid diagram. All the legs are amputated and so on. So let me not erase them. I'm just giving you some guiding instruction of how to find the loops, but I leave that finding the loops as an exercise. So you have other diagrams. For gamma tilde 4 at lambda cube, in this case, one had at the lower level, we had only one diagram, and so we have to find we have to find more loops on that. We have to add one loop on this diagram in various ways. For example, one could add the loop like this. One could add the loop exactly the way what we did earlier, like this. One could replace the vertex here by the 2 vertex. That's one loop. So this is the 2 vertex. And so on. Now there is one more thing here, just like in the for this particular vertex, we actually did not have only one diagram, because the external lines are named and they are distinguishable. So if you interchange external lines, then they are inequivalent diagrams, and that gave us 3 channels. So if you had 1, 2, 3, 4, then you have to add a diagram where 2 and 3 are interchanged, and another 2 and 4 are interchanged. So this is S channel, this is T channel, and this is U channel. So you have to sum over channels also. So you take this diagram. So I'm not adding them, but consider consider summing over different channels also. But when after you add all of them, then divergences, all the poles will not cancel. So maybe I should actually write them as class. Here also. And maybe I should write it as that's a better way of doing it. Now, when you do add all these diagrams, the poles will not cancel. Resulting in that results into the fact that one needs to add another new vertex here at this level. And so new vertex will have to be added at this level, which we will call 3. It's a lambda cube equivalent to 2 loop vertex. And because of that, it will induce another diagram in gamma tilde 2, as we have seen in the previous level. So one has to add that diagram as well. So this vertex is lambda cube, but has equivalent to 2 loops and then 1 loop, 3 loops. And that's a lambda cube diagram. So that's what one has to do. Now, one thing that I will discuss now. So then after adding all these diagrams, there will be all poles will not cancel, and you will also have to add another vertex, 2-point vertex, which is not okay, to absorb the counter term diagram, to absorb the divergences of summing after summing all these diagrams. Now I will now address one point which is very crucial in demonstrating or proving that this process works. The process means adding counter term Feynman diagram, which can be written as a counter term in the Lagrangian. And that happens when the results are all given, the residues of the residues of the poles that that appears as the counter terms. These are polynomials in momentum and mass. Because of if you satisfy that property, then only this method would work. There is another parameter which is lambda. Lambda is just always comes as a prefactor for every diagram, because it just depends on the for each vertex you get a factor of lambda. So there is no problem with the lambda, but the other parameter in the sense of momentum space diagrams, p external momenta and masses appear as parameters. So for these diagrams, so those momenta and masses will have to appear in polynomials in the residues of these poles. But that's not quite obvious because there are log m squared terms and log p squared terms as well. So let us go back and see how log p appears. So yes, here. So the previous order 4-point vertex, this had a finite piece. These diagrams have a finite piece which is given by this, where A is given by the summation over the channels. I must have the expression somewhere here. So this has a logarithm where in the argument z appears, z are st and u. So this is the origin of this is an example of a computation where log p square will appear. Log m square has appeared in many places, we have already seen. Now, if those terms, if you have a at a sufficiently high order, in this actually lambda cube order, it is going to happen because you are adding a loop to this diagram this way or this way. You are adding a loop to this diagram, and that extra loop will produce new divergence, new poles in epsilon, and that will multiply this. And therefore, this will be multiplied with a pole, and therefore will appear as a residue. So that residue, that term will have log p square in it. Just like we had terms where you know, the residue had log m square in it. For example, here in this calculation, 1 over epsilon, the residue has log m h square. Okay. So it is generic that log m square and log p square will appear in the residues of the poles. The question is that if that is the case, then the counter term, this is heavily non-local term from the position space point of view, and there is no Lagrangian for that. I mean, this is non-local Lagrangian. So the systematics of doing that counter term renormalization works only when these residues are polynomial in P and M. Now, we have already, we did not notice it before, but it has happened. It's like a miracle where we added all these quantities, all these 4 diagrams for the 2-point function. You see each individual diagram had log m hat square in the residue. Not this one. No, this is the result. So this 1, 2, 3, 4, these 4 expressions, each one of them had log m square. But in the final expression, log m hat square has cancelled. All these log m hat square cancel. This is the first indication that something is happening here. And this is a general statement in the 3-loop order, lambda cube order. All you will have both log m square and log p square, and although the individual diagrams will contain poles with residue log p square, they cancel when all diagrams are added, and this new counter term diagram is free of such a term. And therefore, so up to this, whatever counter term diagrams we had, we did not have either log m square or log p square. But here there is a chance, because log p square appears. We have seen that log m square has cancelled in a miraculous manner, and this actually is happening at lambda cube order also, though I will not do the full calculation, but this is something that that comes out as a result. Now the claim is log p square and log m square terms appear generically in finite parts. These this results in residues being dependent on such terms at higher level. However, the net counter term is always free of such terms. This is in some sense a statement of a theorem called polynomial residue theorem. Now I will try to arrive at some general structure of the counter terms. And you know, show these things in terms of more technical equations. So let us begin with okay. So in dimensional regularization, so more technical, let me call it more technical discussion. So first, let us point out that in dimensional regularization, the maximum order of pole at epsilon equal to 0 for a graph with a number of loops L is L. For a graph gamma with a number of loops L is L, and therefore in momentum space the expression of the vertex gamma tilde of E, where E is the number of external legs, and will be given by k equals 1 to L 1 over epsilon k R k E P m mu plus a finite piece P by mu m by mu plus order epsilon. And the form of this object, the residue, will be general form, will be m to the power dE lambda to the power v function of L comma E qk E p by mu m by mu. So where dE is the mass dimension, which is also called mechanical or engineering mass dimension. Of gamma. So if it has the mass dimension dE, then one would have a factor of m to the power dE, and then lambda, which is dimensionless, will have a power of v when you give the number of loops. Then when the value of L and E are given, V is given in terms of L and E, as we have seen earlier, and then something dimensionless, and it depends on P by mu and M by mu, because those are the mass parameters. Okay. That should be true also, I think, for the finite piece. So let me just change the equation slightly this way. So this is F finite piece E of P M mu, and this will have m to the power dE lambda to the power v L comma E times curly P by mu. So those are the general forms of the residue and the finite piece. Now, let us first look at why first look at this statement, why the maximum power of 1 over epsilon is L for a L loop diagram. Basically, the reason is that for each extra loop, when you add an extra loop, it increases the power of epsilon, power of 1 over epsilon, if it is a divergent loop. So let me argue that in the next part.